In this video, we'll talk about testing hypothesis about a single linear combination of parameters. And this is best explained with the help of an example. Okay, so sometimes we might encounter situations where we are testing hypothesis about two or more beta j's at a time. So let's take this example and think about this. So let's say we're interested in learning about the returns to education and really distinguishing between what are the returns to a year of attending junior college versus the returns to a year at a four-year university. Okay, so let's say we have a sample of high school graduates, and this is coming from this data set called college, where we are trying to estimate the returns. So we are looking at wages, log wages on the left-hand side. You have JC representing the number of years attending a two-year college, and university represents the number of years at a four-year college. Okay, and then experience is given by how many months you have worked in the workforce. Okay, so if we were wanting to ask the question that are the returns to a year of junior college the same as that of a four-year university, we could state our null hypothesis in such a way. Okay, and we could remain agnostic about what the alternative is. We could write our alternative in this way, or in this way, where we might have good reason to believe that adding a year to junior college is less than a year, adding a year to a four-year university. Okay, so it really depends on how the alternative is stated. Okay, so remember that the way to construct your T statistic is still the same. We take the deviation of the estimate from the hypothesized value and divide it by the standard error. Okay, so in this case, what happens is we are really looking at two betas, right? The beta hat, if we want to specify it and make it more consistent, we are looking at the beta hats for junior college and university. Okay, so here we can construct the T statistic in this way. We can say what is the difference between, and this you can write this as beta hat junior college minus beta hat university divided by the standard error of the difference between these beta hats. Okay, and so this is coming from this formula. The denominator can be computed using this formula for the variance, but this is how we would test it out. Okay, so let's say that we found that the numerator is equal to negative 0.0176. Okay, so here, if this is the way to interpret this coefficient or this value, is that the estimated return to university is about 1.8% higher, or in other words, the estimated return to junior college is about 1.8% lower than relative to the return on university. Okay, but the question for us is this statistically significant, right? So we've understood what the economic significance is of this. What is the economic significance of this number? But we need to know whether this is statistically significant. Okay, so typically softwares would throw out or spit out a p-value associated with such a test, And in this case, we find that the p-value is 0.395, which is a very high p-value, which basically means that we fail to reject our null, okay? So if the p-value was, depending on the level of the test, if the p-value was less than 0.1 or it was less than 10%, then we would have rejected the null. But if the p-value is greater than 10% or 0.1, then we fail to reject the null. Right? So here we can conclude that, or we can infer that this null hypothesis that says the returns are the same, whether you go to junior college or university, we cannot reject this null hypothesis in favor of the alternative. Okay? So that's the idea here.